Okay, so let's continue our lectures on metaphysics. In the previous lecture, we talked about particulars, objects, and tropes. We said that objects are entities with determinate identity conditions. We talked about the difference between constitutional identity. We said that constitution is not identity, so the lump of clay constitutes the statue, but it's not identical to it. And then we also talked about the other ontological category of particulars, tropes or modes. And we said that they're not objects because they don't have determinate identity conditions, and that was why we couldn't count them. Now, today we will look into the upper part of this this square of four category ontology, more specifically into universals, kind and properties and relations. In this and a couple of other lectures, we need to first motivate why they exist, because for objects and modes in particular, that's not very controversial to claim that objects exist. But universals, because they're abstract, some people think that we might not need them, so we need to first defend why we need them, and then we will go into more details of the relationships that exist between them. So as we said, we have these four categories in our ontology. We talked about objects, we talked about objects and modes at particulars, and now we need to talk about universals, kinds, and relations. And as we said, there are philosophers who work with one category ontology, people who work with two category ontology, and those who work with four category. And then we need to basically defend why is it that these two are not enough to cover the everything that exists. And that's what we will do today. So I will keep checking my camera because not the camera but the microphone, because I realize that sometimes it doesn't work. Okay, so the claim is that we need the abstract, not entities, the abstract categories of kind and properties to understand the natural laws. So what are natural laws? These are the laws and the statements that we gain from, for instance, empirical science, where we usually use this kind of present simple tense to describe something among kinds and properties. For instance, when we say that salt is water soluble, when we say that ravens are black, electrons attract protons, opiate causes sleep, or planets move in elliptical orbits with the sun as a focus. The laws of motion in mechanics, thermodynamics, all of them can be described in this way. We call these natural laws. And the claim is that the only way that we can understand these laws and why is it that they hold is to have these ontological categories of kind and properties. Now, to understand why that's the case, we have to take one step back and talk about deductive arguments in logic. We call an argument deductive when the conclusion follows from premises by logical necessity. That is, it's impossible for the premises to be true, but for the conclusion to be false. For instance, if we say that everyone in this room is Mexican and Alex is in this room, therefore Alex is Mexican, that's a deductive argument. It's impossible for the first and second premise to be true, but for the conclusion to be false. Or in symbols, what we need is that premise 1 for all x, if x is H is a human, and x is R, is in this room, then x is M, is Mexican. And premise 2, Alex is H and Alex is R, therefore Alex is M. So the conclusion follows by logic from premise 1 and premise 2. But that's not the only type of argument that we use in our everyday life. We seem to use another type of argument. This type. This is where this is very common. So let's go through one of them. So premise 1, salt dissolves in water. Premise 2, this is salt. And by salt, I mean just common salt. And conclusion, therefore, this salt, this crystal salts, dissolves in water. This is very common, right? Like, imagine that someone doesn't know that. Like, they want to pour some salt in the water, and they say, like, if I do this, will it dissolve in water? And then we say, what is that? Is that salt? And they say, yeah, it's salt. Yeah, salt dissolves in water. It's okay. Or they say, is it okay if I mix these two? Will they mix? What is that? Is that water? Yeah, they mix together. It's fine. So we have this type of argument all the time. That's also a good exercise. Just think about all different ways that we use these things. Like, what kind of pot is that? That's not a good pot because the handle will get hot. Why? Well, the handle is made of copper, and copper it gets really hot. It conducts heat very well, so that will get really hot. That's, again, another argument in this form. And I don't see it as controversial to assume that this type of argument works. We use it all the time, and we believe that it works. It makes sense, total sense to us. So if someone wants to say, no, this is not a valid argument, the conclusion is false, then they have to explain exactly how it is false, why is it that we believe that is true, and how we should correct it, what's the correct conclusion is. But I will assume that this argument works and you agree with me that it works. And the question is basically why it works. Because this is not logic. This is not a deductive argument. If you write down everything, the premise 1 says that S, that is salt, is WS, water soluble. Premise 2 says this is S, and conclusion is therefore this is WS. But this is not a deductive argument because the is in the first argument, in the first premise, and the is in the second premise are not the same is. The first one is just a characterization. It says that kind salt has this property of being water soluble. But the second is an is of instantiation. What we're saying is that this particular object is an instance of the kind salt. So these are not the same is. So it can only work and we can only get to the conclusion if we do a fallacy of equivocation. Otherwise, this doesn't work. In other words, the conclusion does not follow by logic and reason from premise 1 and premise 2. So why do we think that it holds? And if it holds, why does it hold? Like, how does it work? Because this is not at least deductive argument, right? Now, there are different ways that we can try to resolve this issue. One way that people have tried doing this is through all statements. And all statements says that it is indeed follows from logic, the conclusion, because the first premise, when we say that salt dissolves in water, we basically are saying that this all statement, that all salt crystals dissolve in water. That's our first premise. And the second premise is that this is a salt crystal, and the conclusion is therefore this dissolves in water. Now, if this is what we mean, indeed, from the first premise, then this works. This is a valid argument. If premises are true, then the conclusion follows. But of course, now we are making a claim that is not clear that much, that all salt crystals dissolve in water. How do we defend this? Notice that this is basically a translation of a natural law. As we said, that when we say salt dissolves in water, this is the statement of a natural law. So when we say that all salt crystals dissolve in water, if we're translating this natural law in terms of this all statement, then we need to defend how is it that we have come to this conclusion that all salt crystals dissolve in water. Okay, someone might argue like this. They might say, we have seen salt crystals dissolve in water numerous times. Premise 1. Premise 2, nature is uniform. And premise 3, therefore all salt crystals dissolve in water. Okay, I mean, the validity of this argument depends on what we mean by uniform, and that can be an issue on its own, but let's suppose that you can actually fill in for the uniform in a way that the argument is valid. But we still need to justify this premise too when we say that nature is uniform. Does that hold? How do we know that premise is true. And someone might say that, okay, what about this argument? We have seen nature to be uniform, therefore nature is uniform. And of course, that argument doesn't work, obviously, because there is a hidden assumption there. And the assumption is that nature is uniform, right? So the argument to work, it should be we have seen nature to be uniform before. And since nature is uniform, therefore that uniformity of nature is uniform, therefore nature is uniform. But of course, that just begs the question, right? As David Hume says, to endeavor the proof of this, and by this he means the uniformity of nature, by probable arguments. And by probable arguments he means the type of arguments that I just said. The salt dissolves in water, this is salt, therefore this dissolves in water, must be evidently going in a circle and taking that for granted, which is the very point in question. Of course, you cannot prove the uniformity of nature by uniformity of nature. That just begs the question. So if we backtrack everything, if this premise is not true, if this is not true, then the conclusion is not true. If the conclusion is not true, this all salt crystals dissolve in water is not true. So that original argument fails. So it seems that we just have to have a kind of faith in the uniformity of nature. Hey, we've seen it work all the time. We don't have any reason for it, you see, because we can't provide any argument for it. We just have to have faith that it's just the way it is. But that's not a good way. That's not a good way of dealing with it. As we said, it's just based on faith. It's not based on any argument. So another way that we might see a problem with the all statement, not only do we not have a good argument for uniformity of nature, we actually seem to have exceptions to it. So these all statements, they have a very big claim. They say like all crystal salts dissolve in water, all ravens are black, or all humans have eyes and can see. But that's not true, because we do have exceptions. We have albino ravens, we have humans who are born blind, we have some freakish salt crystal that doesn't dissolve in water. We do have exceptions. So saying all is not completely true, because if all means all, we're dealing with logic here. There's no vagueness there. You say all, it means all, but this is not all, because there are exceptions. Someone says, okay, yeah, but when we say all, what do we mean? Like all normal ones, putting aside those exceptions and those freakish examples. What we mean is basically all normal salt crystals dissolve in water, or all normal humans are born with the ability to see, or all normal ravens are black, if you put aside the genetic mutations and everything. The normal ones, they follow the law, but we face a problem here, because what do we mean by normal? It seems that normal exactly means being according to the norm or the natural law. In other words, being normal already assumes a norm, and that cannot be used to identify the norm. You see, so the norm is the natural law. We're asking, okay, how do we explain that? How do we defend that natural law? Now, if you come down and then say, okay, the reason that we say that norm holds is because all normal ravens are black, then we say, okay, you're already using the normal. What do we mean by normal ravens? You mean the ravens that follow that natural law. But you're trying to defend that natural law. You cannot use the natural law to defend itself, or you cannot explain natural law in terms of which uses natural law. So this cannot work. We cannot say that all normal ravens, because again, then you have to explain what's normal, and then you will go in a circle. Someone might attempt it in a different way. They might say, okay, no, wait a minute. When we say all, we don't mean like literally all. What we mean is about the probability. When we say all, we basically mean most probably a salt crystal dissolves in water. It's not all salt crystals, just most probably. Like most probably a raven is black. And this might, I mean, at the first glance, it might look, okay, it's pretty good, right? It makes sense. Like, we've seen salt dissolve in water so many times that it makes sense to assume that the next time it will also dissolve in water. So basically, it comes from the probability theory. Remember, if you had like a big bag of balls, and then suppose you had two different colors, blue and red, and then you drew 10 balls randomly, one after each other, and they all come out blue, then probability theory tells you that it's reasonable to expect that that big bag of balls has lots of blue balls. Actually, I selected a different color for the ball, but anyway. So if you pick out randomly and all those 10 balls come out blue, then there is a very good chance that all the rest are also blue. So which means that the next one that you pull out, the probability is very high that the next one is blue. You can show that mathematically, right? The probability theory has that. And this also allows the possibility of exceptions, because you might, of course, the probability is not 100%. It's not like we can claim that every single one of them is blue and every single crystal salt will dissolve in water. It's just a probability, so there might be some exceptions. So we might, this looks perfect, right, to this problem. But there is actually a problem here. The probability theory works based on certain assumptions. And if those assumptions are not satisfied, then those theories, the results that they give us, is not correct. One is we have to draw randomly from that big bag of balls, but we don't draw randomly from nature. Now I will come back to these details, but let's just focus on these assumptions. We don't draw randomly from nature. And what happens if we don't draw randomly from that big bag of balls? Like, suppose that we have 1,000 balls, like 990 of them red, 10 blue. But you don't draw randomly. You draw it in a certain pattern, or only, for instance, on top of the bag. And I've put all the blue balls on top and all the red in the bottom. You will draw one by one, and you will see blue, 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 blue. And after 10, I tell you, okay, what's the probability that next ball is going to be blue? And then you use your probability theory mathematics, and you say, oh, yes, the probability is going to be really high. I mean, not really high, but I mean, there's a very good probability that the next one is blue. But in actuality, in fact, we know that the probability is 0 because all the rest are red. So why is it? Why is it that we get a bad solution, a wrong solution here? Well, because the assumption doesn't hold. We said we're going to draw randomly, but we're not drawing randomly. If you had drawn randomly, then you would have seen some red balls also coming out, and then you would say, okay, then actually more red would come out, and then you would expect more red balls in the bag, as it is the fact. But we don't draw randomly from nature. It's not like that we get some crystal salt from this place, and then something from another random place, and then from another random place, and not only also in a space, but also in time. Like, not only the salt that is created in this age, but maybe from 100 years before and then 100 years after. We're not drawing randomly from space and time these salt crystals to be able to claim that, hey, we gathered like 1,000 different species randomly selected from different places in space and in time, and we gathered and we tested all of them. They dissolve in water, therefore, through probability theory, most probably salt crystals dissolve in water. We don't do that. So that assumption doesn't hold, so we cannot really use the probability theory. 2, another assumption is that the bag of balls has a finite number of balls. That's why probability theory works. If you increase the n to infinity, that wouldn't work. And it's the same thing, like how many crystal salts exists in space and time. Because remember, the laws that we define, it's timeless. I mean, might change, but when we say that salt dissolves in water, we don't mean that in 2024 it dissolves. In 2050, I don't know, people, they have to do the experiments all over again because it might have changed. No, we have this confidence that the law is a general law. I mean, the salt might change, but if it is the salt that we have today, then it will dissolve in water. But how do we know that? If the number of salt samples can be infinite, which it is infinite. I mean, if we assume that the age of the universe that's not metaphysically impossible, right? That the age of the universe is infinite, and we have a salt making process going on, if not on Earth, on some other planet, we will always have something, right? If not salt, some other thing, some other natural law governing the gravitational fields. They will still hold. So the sample space is going to be infinite. So this analogy of removing balls out of that bag wouldn't work. This, but in addition to all of this, the biggest, I believe, disadvantage of this form of viewing all statements from natural laws is that it seems that the repetition of experiments are claimed to be because of this probability. Like when we repeat an experiment, we do it in the same sense that we draw balls out of that bag, as if we're trying to increase the probability by resampling. But is that really the case? Because if you remember, like we not if you remember, but I mean if you think about it, we do have experiments that are very expensive, and we do it only once. If this analogy if this is true, if this is the way that we get natural laws, then it doesn't make sense at all to spend millions of dollars on doing experiments that we can only do once. Because that's like spending millions of dollars of drawing just one ball that is not even random out of a bag that is not even finite, and then try to claim a natural law based on that. What kind of information can we get out of it? It doesn't make sense, right? We don't repeat experiments because we want to increase the probability. There's a different reason why we do it. So as I say here, I go into a little bit more details about the fact of probability assumptions. Let's say that the probability that this salt crystal dissolves in water is 1 in 10 to the power of 100. If that's the case, then we cannot really say that the all statement is true. We cannot say that most probably salt, because that's not most probably 1 in 10 to the power of 100. But the point is that this can be compatible with our experimental results. There's nothing wrong with that. It can be compatible because those two assumptions of probability theory does not hold. We're not drawing randomly, and the sample space can be infinite. So because if you have a big ball with potentially infinite number of them, that by above probability there will be infinite number of blue balls. Since we're not drawing randomly, we might get any of number of them in a row. So this probability is completely compatible. So experimental results cannot give us what we want. Regarding the other point, which I think is the main critical point, we do not repeat experiments for the sake of probability theory. We do so to reduce our errors. Errors in misidentifying what we have. We have an object and then we say, okay, this is common salt. We repeat the experiment because what we have might not be common salt, or might not be the pure common salt that we think. So we might be misidentifying what we think we have, and repeat to make sure that what we have is really pure salt. And 2 is errors in our measurements and observations. The tools that we have, they might make errors. So we repeat experiments to make sure that we don't have errors in our measurements. The point is that if we know that we're not making any mistake, if somehow God tells us, hey, like this experiment, everything is perfect, what you will measure is exactly what there is, then it seems that even one good experiment can give us a great deal of information. And of course, this is indeed what happens with expensive experiments. That's how we justify it. Why are they expensive? Because we are making tools that are so sensitive that the data that we get is very good. We're using very, very sensitive sensors, very expensive ones, because we have to make sure that whatever we measure to the best accuracy that we can. We have to make sure that we're not misidentifying anything, we don't have any measurement errors, everything is perfect. Because we do know that if that's true, even one experiment would be enough to establish a natural law. If we find a new particle and then we make sure that everything is perfect, and in that particle you put it in a field and is attracted to the positive field, you can establish it as a natural law that this type of particle is attracted to the negative charge. But if this kind of almost probably statement or translation of natural law were what we actually do, then we are in no place to claim such a big claim. You're just doing it once. How can you claim that most probably then the next particle of the same kind would also be attracted to the negative charge? We can't. So we see that probability statements also cannot really give us what we want. This is a dead end. For the induction arguments, that's why it's called the problem of induction. But there is not really a problem of induction. It only becomes a problem when you translate or you try to translate those natural laws into these all statements. And that's where we hit a rock bottom. So again, salt dissolves in water. This is salt, therefore this dissolves in water. This is a very common argument. Everyone agrees that it works. We just don't know why. David Hume says that the connection between these propositions is not intuitive. There is required a medium which may enable the mind to draw such inference, if indeed it be drawn by reasoning and argument. What that medium is, I must confess, passes my comprehension. So Hume says, I know that it works. We can agree that it works. That's not the big issue here. And we also know that it's not a deductive argument. So it's like something must be there. Like there must be some kind of reasoning going on here, but I don't know how. I don't know how to do this. Because as we saw, it's not easy really to explain exactly why is it that this argument holds, and more specifically, how are we to understand this first premise, the natural law, to make sure that this whole thing works. And as we saw, the all statements, which is a very popular version, does not work well. Bertrand Russell says that if you're challenged as to why we believe that the sun will continue to rise as heretofore, we may appeal to the laws of motion. The earth, we shall say, is a freely rotating body, and such bodies do not cease to rotate unless something interferes from outside. And there's nothing outside to interfere with the earth between now and tomorrow. Of course, it might be doubted whether we are quite certain that there's nothing outside to interfere, but this is not the interesting doubt, and the quote continues. I will show the rest of the quote, but let's understand what he says. So he says, if someone says, hey, how do we know that the sun will rise tomorrow? And then you go to the laws of mechanics and they say, okay, this is moving. If nothing interferes with it, it will also raise, right? And then someone says, okay, maybe something hits the earth, maybe a sun explodes. Yeah, okay, that maybe, but that's not the interesting doubt. There's actually more interesting doubt. The interesting doubt is as to whether the laws of motion will remain in operation until tomorrow. If this doubt is raised, we find ourselves in the same position as when the doubt about the sunrise was first raised. The only reason, and this is important, that Bertrand Russell says, that the only reason for believing that the laws of motion will remain in operation is that they have operated so far as our knowledge of the past enables us to judge. So Bertrand also believes that the only reason that we can say that the laws of motion will hold tomorrow is because, they have been holding up to now. And that's the kind of all statement way of looking at the natural law. Like we have seen that it has worked up to now. Either we can say that that means they work all the time, even though we don't have any reason for it, or we might say that it's because of uniformity of nature, even though we don't have any reason for uniformity of nature, or we might say that it most probably will give rise to the law of motion tomorrow, which again we don't have a very good argument why it's most probable. So basically we don't have any good argument why it would if that doubt is raised, we're stuck. There's not much we can do. But that's the problem with all statements. And the claim that we make is that, look, let's suppose just that this argument is true as it is. Let's go to the original form that we had, and that was the salt dissolves in water. This is salt, therefore this dissolves in water. Let's suppose that this holds as it is, and just see what does this thing imply. If this is true, if this argument is valid, this implies two things. First, it implies that these premises are true, that salt dissolves in water. But what does that premise says? The premise is talking about an ontological relation between two relatas. It talks about salt, which is a universal kind, and it talks about water or water solubility as a property. But the point is that if that premise is true, if such a relation exists, then it means that the relata of that relation, that is the salt and water solubility, must also exist, albeit they are abstract categories. They're abstract kinds of things and abstract properties. Nonetheless, we have to assume that they are things. They are real things in the inventory of reality. And there is this kind of relation between them of characterization, of salt being characterized by water solubility. So if we accept this argument, then we have to accept that universal kinds such as salt and water and solubility exist, even though as abstract entities. So that's the defense of the existence of universals and against nominalism, that the only proper way of explaining natural laws is to include universal kinds and properties as abstract entities in the inventory of our reality. And two, this is something that we do in next lecture, try to explain the connection that this whole thing, this argument, in terms of these things, these new entities that we explained. And that's something that we will do next lecture. We will explain the connection between a particular salt, the universal kind salt, the natural law, the empirical data, the exceptions, and the intuition that we have for this argument. If we can do that, and as we will see in the next lecture, we can easily do that, and it's a very neat and beautiful way of solving this problem, then that justifies to assume that the universal kinds and properties also exist, and that will justify the four-category ontology as necessary and sufficient to explain everything that we see in nature. But that's something for the next lecture.